And we have to start. And today we will continue to study the notion of the local time. We will speak today about the expressions for the local time. You remember, last time we considered interesting example. Last time we considered example of the following kind. We discussed when a process Wt when t is from the interval 0, 1, and we consider such function h epsilon of x, which was equal 1 to epsilon, indicator of the interval y0 minus epsilon, y0 plus epsilon from x. Then we considered the following integral h epsilon of yt wt dt denoted by eta epsilon, and we proved that it converges at least in a sense of A2 under epsilon tends to 0. It converges to some eta 0. We already have a name for this limit. We said that it is a local time. Local time. At y0 of the Wiener process, and moreover, we have a formal notation for this object. This formal notation was motivated by the following relationship for the function h epsilon. You remember that last time we mentioned that for every function f which is continuous and bounded on R, we have the integral with respect to R h epsilon of x multiplied by f of x dx tends to f of y0 when epsilon tends to 0. And we remembered that in physics, in mathematical physics, and in the theory of generalized functions, people consider such a functional which put into correspondence to continuous function its value in some point. And even they have a notation of the following kind: delta y from f, it is by definition equal to f of y. And this expression, this functional, which give for arbitrary continuous bounded function its value as a fixed point, is called delta function at that point. Using this notation, one can say, instead of these long formulas, one can say simply that H epsilon tends to delta at point 0 when epsilon tends to 0. Then, if we agree with this, at least on the formal level, one can use a good notation for the limit of eta epsilon. The integral h epsilon of wt dt tends to integral from 0 to 1 delta y0 from wt from delta y0, let's write it here, delta y0 from wt dt when epsilon tends to 0. And we will speak today about this object. We have seen on the last lecture that such limit exists not only for linear processes, but for example, for deterministic smooth function. We already have an expression for it. So today our object is a local time. Let us write the title of the lecture. Expression local time for Gaussian random field. We have seen last lecture that maybe it is good to work with such functional in order to answer questions like does our random process or random field visit some fixed point? So let us recall this general problem. We consider a random field which is defined on the sum domain in Rg and is acting in Rn. Here is excuse me, not Rg but Rn. I will suppose that n is less than m. And we are looking for probability that our random field will visit some fixed point. So we consider such a probability. Y0 now. Put here vector because this is a vector case. And we want to say something about this probability. At least, is it positive or not? And as we have seen, it is maybe it is useful now to define such object. I will write it formally. A at the point y0, which is formally integral with respect to d, delta y0 from psi of u du. So If we will be able to define this object properly, if it exists, and have non-zero expectation, it means that this probability must be positive. We already discussed. So let's try to understand what is. Of course, one can proceed exactly as in the one-dimensional case for Wiener process. So one can try to organize the same procedure. So we will consider function h epsilon from the point x. Now this x is from Rd, the same as y is u, which will be equal 1 over, here is a constant which depends on m. This constant is the volume of the ball of radius 1 in the n-dimensional space. It does not matter what is it. Just some constant, some positive constant. Here is epsilon m power multiplied by the indicator. Now we have not an interval, but a ball of radius epsilon around the point y0. So now we have such an expression b y0 epsilon. This is a ball of radius epsilon. This is center y0. This is its indicator from the point x. So construction is exactly the same. You remember, we have the interval, we take the indicator of the interval around of this point and divide this indicator on the length of the interval. Now we have the ball around of the point and we divide on the volume of this point. So one can imagine that this function in vector case have exactly the same property as before in one-dimensional case. So please check this as an exercise that for all function f, which is continuous and bound on the space Rm now, the following relationship holds. We have integral with respect to Rm here h epsilon of x multiply of f of x dx tends to value of f at the point y0, where epsilon tends to 1. So this can be checked very easily just using the continuity of the function f at the point y0. Please do it. After we have this relationship, one can again write it in short way using theta function, and one can say that now h epsilon tends to theta at the point 0, where epsilon tends to 0, and after this we can organize such an integral d h epsilon from psi of u du. You remember, it is exactly as in our example with the Wiener process. We just substitute Wiener process by the random field psi Then we have to substitute the interval 0, 1, where the winner process was defined, by the domain D on which our random field is defined. But everything in the procedure looks like the same. After this, one can try to check that there exists a limit, at least in this is a problem. One can try to check that there exists a limit, and we will define this limit, denote this limit again as follows. From psi of u du, and then we can say that this is a local type of our random field psi at the point y0. And if this local type exists, has non-zero expectation, then we can say that our psi random field psi visits this point y0. This is a good general program, but usually when you have general receipt, it has a lot of troubles when you want to apply it to some concrete situation. So today we began to think about these problems, and our aim today is to understand the structure of this limit, if it exists, how one can discuss this random variable, because it looks strange. Inside of the integral, we have the application of theta function to random variables, random vector. So it is non-usual expression from the point of view of probabilities. So let us begin our investigation with the useful understanding that now we have something familiar to us, because it is always good when you study new mathematical subject to find something which looks like this. And I insist that we already have such situation even in SIP university course from analysis and measures. So let us discuss visitation measure. Visitation measure for random field psi. What are going to do? Let us consider arbitrary Borel subset A, which from R. This is a Borel sigma. Borel sigma. So for those who don't remember exactly what is Borel, this is just all good sets which you can imagine in RL. Formally speaking, it is sigma field, the smallest sigma field which contains all open set. So it contains all rectangles, triangles, balls, whatever you can imagine. Every good set is here. Only some ugly, non-measured construction we can construct it artificially, but it is not interesting. So we just take this set from Rm, consider the following expression. Consider the following expression: mu of A, which will be equal to integral with respect to d of indicator of the set A from psi of u du. This integral is properly defined. D is a bounded set, so everything is well defined. And we can consider this expression as a function of A. So now what we have? We have now a random mapping mu, which is acting from B R M to the set of non-negative numbers. Even we can put here lambda n of D. The biggest value which we can get here is obtained when we put here just one instead of all of this. Then we have integral which is respect to d of 1 du, which is equal exactly to Lebesgue volume of this domain D. So our random map mu takes its values in this interval for sure. But now, due to this special expression for mu, I can say that mu is not an arbitrary map from here to here. I am claiming that mu is a measure. Mu is a measure. Mu is a measure. It means that it is non-negative. It is sigma additive. Now let's check. Of course, everybody understands that mu of the empty set is equal to 0 because the indicator of empty set is 0, and we have here integral which is also. Now let's check that mu is sigma additive. What we have to check? We have to check the following relationship. The following relationship. Suppose we have a family sequence of the Borel subsets which are disjoint pairwise. So A and is not a good letter here because our spaces are M. Let's put here a K. K is the 1. And we suppose that AK has empty intersection with AJ when K is not equal not equal to J. What we have to check? We have to check the following relation. That mu of the union from k equal 1 to infinity of a case is equal to the sum from k equal 1 to infinity mu of a. Let us try to check this using this expression. Let me write mu of this u by definition. So what I have to write, mu of the union, mu of the union k equal 1 to infinity k is equal to, here is indicator, and here is the union of k equal 1 to infinity k of psi of u du. Now let us recall that these sets are disjoint. Due to this, the indicator of the union is equal to sum of indicators. So I can continue the formula and say that it is integral with respect to d. Here is the sum from k equal 1 to infinity indicator of a case from psi of u then u. Last step which we have to do is to interchanging of the order of the integral and the sum. And we can do this because everything here is non-negative. You remember such variable visitation when you can interchange summation of integration in any order whatever you want if the function under the sign of integral or summation is non-negative. So due to this forbidden theorem, I can say that it is equal exactly to the sum from k equal 1 to infinity integral with respect to d indicator of a k with psi of u du. And one can see that the summands in obtained series are exactly mu of a k. So I can say that this is equal to sum from k equal 1. This is equal to sum. Let's write it here. From k equal 1 to 50 mu of A.A. Actually, this is more or less what we wanted. Only one problem exists here, because this Fubini theorem tells us that equality holds everything. Yeah? So I have to put here this. And due to this circumstance, we need some extra technical arguments, but they can be done. I don't pay attention to these extra arguments because they are rather technical and do not bring us new knowledge now about the visitation measure. Then we can say that mu is a measure. Measure here is important under fixed omega. Under fixed omega from. Okay. So now we have such random measure. This random measure is called visitation measure. It is visitation measure. Visitation measure. For example. And it occurs that this measure is related to the notion of the local time. Why it is so? Let me recall you that when we study measure on the Euclid space, if U is a measure on Rn, then the natural question is the following. Is mu absolutely continuous? Continuous. With respect to the back volume, to lambda n, the back volume, that's R. This is a very natural question, and especially for people who remember their studies at university, when you firstly discuss the notion of the random vector, the question about the distribution of random vector arises, and it occurs that you better work with those vectors which have probability density. So the probability to be absolutely continuous formally looks very easy. It means that
对，就这个意思。
I'm sorry, Professor.
Excuse me?
Oh, sorry. We don't hear.
But what about now?
Now it's okay.
Now we can hear. Yes.
Yeah, okay. Have I repeat the definition of absolute continuity?
Yes. Yes.
Okay.
Yeah.
So what does it mean on the formal level? The definition of absolute continuity. It means that if for some set H, Lebesgue volume is equal to 0, then we must have the same for our measure. This is just formal requirement. It allows us to exclude some cases when mu is concentrated, for example, in several points or on some line, on some hyperspace, hypersurface, and so on. But it is interesting. Then, if answer is positive, so if it is so, if mu is absolutely continuous, then it has density. It has density. Density. What does it mean that it has density? It means that there exists such function p from Rn to 0 plus infinity that mu of H can be represented as an integral with respect to H of p of x dx. So exactly the same property as we mentioned when you study the density of distribution of random vector. So if mu is absolutely continuous, then it has the following representation. So suppose now that mu is absolutely continuous. Then there exists the following fact from measure theory. It's called also a Lebesgue theory. For almost all x belonging to Rm, so excluding subset of Lebesgue volumes, we have the following. And here our function h epsilon came into play. You see, the integral with respect to Rm h epsilon of x minus let me put here y0 because we defined our h epsilon based on this form here of x mu dx tends to p at y0, epsilon tends to 0. You see? So Now we understand how we can interpret our local time, because this expression, the integral of h epsilon with respect to mu, can be written as follows. I just recall you definition of mu. Mu of A is equal to integral with respect to d, indicator of h of psi of u du. Psi of u. So the integral Rn h epsilon of x mu dx is equal exactly integral with respect to d h epsilon from psi of u du. You see exactly the same expression when we define our local time. So, if we are able to prove that our visitation measure is absolutely continuous, then probably our local time is just density of visitation measure. It is a very good relation, very good understanding what is the local time, but you see here this words from Lebesgue theorem, and it is usual that from the theorem which is formulated in the right way, we cannot just take out some rules. When we do this, theorem becomes not true. But we can add some extra conditions. Suppose that P is continuous. If mu is absolutely continuous, and P belongs to set of continuous functions on Rn, then for all y belongs to Rn, we have such conditions. It means that in this case, our local time is nothing else than the density of visitation measure. Let's write this conclusion by words. In this case, the local time under the conditions which we mentioned, I don't rewrite this condition, we just have it, is a density of visitation measure. Is a density of visitation. But due to this, we understand now that in this case, when a visitation measure has continuous density, local time exists for any point. Of course, it can be equal to zero. It can be equal to zero. In this case, we do not hit. Maybe we don't hit the point, but at least it exists. And we remember that we denote the local time y0 is a local time. At the point y0, and it is density. So we have the expression. That integral Rn of f of x mu dx will be equal because mu has a density which is local time, will be equal to integral with respect to Rn f of x. Here is L of x. Now I use notation L for arbitrary point because you remember our theorem says us that now it exists at any point. Dx. To finish this good formula, just recall what is this. Let me rewrite it. We already did this, but it is useful to do it again. So integral with respect to Rn f of x mu dx is equal to integral with respect to d f of psi of u du. And now let's unite together to this equality. We will get final relationship for a local time. Sometimes this relationship called visitation formula. So the integral with respect to d of f of psi of u du is equal now, excuse me, somebody is calling me. Алло, да, Сергей Иванович. Вы знаете, у меня сейчас лекция буквально через 10 минут. Is equal to integral over Rn f of x ax dx. This is visitation formula. Okay, so we have such a relationship which gives us information. What is the local time? You see, in this expression, there are no delta functions, there are no some mystics. Yeah? We just do work with the measures and so on. So in this way, one can think that local time is just density of visitation measure. But the problem still remains. We still don't know how this random variable looks like, how one can discuss it, in which terms. You see, of course, for some special cases, and we will see such cases in the future, for example, in process, Mark Katz produced a very good formula for moments of the local time and so on. So there are a lot of properties of local times investigated already. But still, it is non-clear, at least from the first look, how one can define, how one can check this random variable to work with it. And now we go to the case in which we can do this for sure. This will be a case of Gaussian random field. So, in order to work with this local time, we firstly consider a case where psi is Gaussian random field. So, now I'm supposing that psi is a Gaussian random field. What we can say in this case about the psi and functions. To understand this, let me recall very briefly, because we already have experience about Gaussian distribution. What is Gaussian now? Yeah? So we say that psi has a normal distribution with parameters A and sigma squared if it has a density P of U equal 1 square of 2 pi multiplied by sigma and exponent of U minus A squared divided by 2 sigma squared. Yes. This is Gaussian density. It occurs that expectation of psi is equal to A, variance of psi is equal to sigma squared, and characteristic function of psi expectation of exponent of imaginary unit t psi is equal e a minus 1/2 of t square sigma square. These are just recalling what is one-dimensional Gaussian distribution. Then let me recall you what does it mean multi-dimensional Gaussian vector. So we say that maybe eta is equal to eta 1, eta n is a Gaussian random vector. So random vector with parameters h and sigma. Now h here h belongs to Rn and sigma is Rn and matrix. Then Then we have, if we have the following characteristic function, exponent of the E lambda multiplied by eta is equal to E, here is E lambda H minus 1/2, and here is quadratic form sigma lambda lambda. Or excuse me, it's better to write it here. Minus in the sign of exponent 1/2 of quadratic form sigma lambda lambda. I use this characteristic function because it occurs that Gaussian vector not always have a density. It have a density only in a case when this matrix, which evidently must be non-negative defined, when it is strongly positive. So when the determinant of this matrix is positive. In this case, one can say that our Gaussian vector has density, and this density can be expressed as follows: P of x is equal to 1 of square, here is 2 pi multiplying the determinant of sigma, multiply on the determinant of sigma in power oh, excuse me. I wanted to write it universal. Okay, 2 pi r over 2, and here is square root of determinant of sigma. Okay. Here is it, and here we write the exponent 1 minus 1/2 and quadratic form. Since again, maybe it's better to write it here. Exponent minus 1/2 of quadratic form. Since sigma is positive, we write here. We can write here sigma minus 1 from x minus 8, x minus 8. Okay. This is the density of our Gaussian vector. And finally, we will call our random field psi is Gaussian if any finite sets set of its coordinates in different points is Gaussian. Random vector. This is a definition of fields, of this set of fields, which we will use in our work for the next lecture with the local types. For today, we finished our work. Thank you for attention, and maybe somebody has questions, please.
So if there is no questions, thanks everyone, and maybe see next
We
time.
will meet next Monday. Okay.
Yeah.
See you. Bye.